Okay, welcome back. This is the third of our videos looking at bounding probabilities. So far we had the tail sum, which we could take expected value and write it as a sum of greater thans. We had Markov, which we could get a probability that a random variable was greater than a constant in terms of the expected value in that constant. And now we're going to do the classic one, which is called Chebyshev's. And what Chebyshev's will do is it will give us the bounding probabilities using both the mean and the variance. And again, let's recap the idea. We have a distribution, a random variable, but we don't know its distribution. And we're just saying, well, what's the sort of worst case scenario can at least bound my probabilities? So let's look at Chebyshev's. So here we are, we've got a random variable. It has an expected value of, we'll denote as mu, but just remind you, this is just a shortcut for the expected value of y. And we've got a finite variance sigma squared, so again, this is the variance of y. Then we're going to have some non-negative, non-zero constant, k. And we can say that the probability, there's two versions. There's the first one which says, what's the probability that basically y minus mu, the absolute value, is less than k sigma? Or we can say, what's the probability that it's greater than or equal to k sigma? So, again, like last time, we'll start with the proof, and then we'll do an example. So let's look at the proof first of all. Well, there's multiple ways of doing Chebyshev's. You might have seen some others, and there's a discrete version, there's a continuous version. But since we've just used Markov's inequality, let's see if we can use that. So, again, let's start off with our standard at the left. Now, I don't know about you, but I find absolute values hard to deal with. And the best thing we can do is we can square it and get rid of it, because I can deal with squares. So what I've done here is we've just squared both sides of the inequality. It hasn't changed the inequality. So now what we have, instead of y minus mu absolute, we have y minus mu squared. And in this time when we squared it, we had k squared sigma squared. Now, we've got, the probability that some, in this case, this is some random variable, and this is some constant. And we're doing a greater than. So it's starting to look like we could use Markov inequality. Well, let's formalize that. First of all, instead of worrying about this whole random variable here, let's just give it a name. So we will let x equal y minus mu squared. If you take a random variable, you take off a constant, you square, you still have a random variable, just give it a name, x. What about our constant? Well, it's complicated, isn't it? But it's this, it's a k squared sigma squared. So now we have this stated fact, which is our Markov inequality we saw last time. The probability that x is greater than or equal to a is less than the expected value of x over k squared. Well, what is the expected value of x? Well, the expected value of x equals the expected value of y minus mu squared, which you should hopefully by now recognize as the second moment around the mean, or what we call the variance of y. And we're using that, it's denoted as sigma squared. So, in here, I can represent this as sigma squared. What's k squared? So that shouldn't be k squared, I do apologize. That should be a. So in that case, we now put our a in, and our a will be k squared sigma squared by our definition. So now I can divide by our sigma squared. Notice I'm assuming that sigma is not equal to 0 here. We're assuming we don't have what we call a degenerate random variable, that is no variance. So I can divide. If not, I couldn't do this at this point, but I can, and that gives me my 1 over k squared. Okay, so now we've got that, let's use it. So, the number of customers at a shop in a day has a mean of 20 with a variance of 16. What is the lower bound on the probability the number of customers will lie between 12 and 28? Well, let's write down, as always, what we've got, and then we'll go from there. So what do we get? So far, we know that the expected value of y, which is the number of customers, is 20, and the variance of y equals 16. And what do we want? We want the probability that y is less than 28 but greater than 12. Right, so how do you approach these? We're going to manipulate this so we get one of the left sides of that Chebyshev's inequality. So the first thing I'm going to do is I'm going to take this inequality inside, and I'm going to take off a number off all the parts. And the number I'm going to take off is the expected value. So I'm going to say 12 minus 20 is less than y minus mu, because that's this, remember, is mu, which is less than 28 minus 20. So for each part of each side of the inequality, so for each one of these, I've taken off the same value, so it doesn't change the inequality at all. So what can we do next? Well, let's just simplify this. This is going to be the probability that minus 8 is less than y minus mu, which is less than 8. That's a good sign that I've set up this problem right, because it works. We've got basically the same distance on both sides. We've got 8 and minus 8. So we can write this as the probability that y minus mu, the absolute value, is less than 8. So we've already got a bit of the sort of the Chebyshevs, but let's continue. I can write this as it's the probability the absolute value of y minus mu is less than 2 times 4, because that's what 8 is, which is the same as the probability that y minus mu is less than 2 sigma. Why? Because we know that the variance of y equals 16. So sigma squared equals 16, so sigma equals 4. So now if you look at this, you'll notice that this is our k. So our k equals 2. So we know that this thing here must be greater than or equal to 1 minus 1 over k squared, which is 1 minus 1 over 2 squared, which equals 1 minus a quarter, which equals 3/4. So I know for this particular thing, the probability that y lies between 12 and 28 exclusively is basically greater than 3/4. Simple as that. Okay, so there's our bounding probabilities. That'll be the videos for this week. Next week we will continue with discrete random variables. Remember, if you haven't already looked at it, there's information online, all the tutorials, the consulting, etc. is now online. If you're not sure what you need to do, etc., contact me either via Piazza or email me. The main thing you can do at this point is the tute questions for tute 2 should be out. Have a look at them, have a go at them, and if you need any support, go and look at the announcement. It will tell you there's various supports available for you. Okay, have a really good weekend, and I'll see you next week.